So we have two small charged spheres hanging from cords of same length, which is L, and they are making small angles θ1 and θ2 with the vertical. Charges are given Q1, Q2, and masses are given M1 and M2. And you would like to determine the ratio θ1 over θ2, and we would like to estimate the distance between these two charges, okay? So I wanted to redraw this picture with a little bit exaggeration. So I assumed M1 is less than or equal to M2. And in this case, I said, since this guy is heavier, it should pull down a little bit stronger. So this one should be lower than this one. So I thought this length is same as this length, and they have some tension like T1 and T2. They have electric charges Q1 and Q2, so there's like a force on this guy by the other guy, and there's another force on this guy by the other guy. And yesterday we talked that they should be equal and opposite, and there's like M1G and M2G. And I said, let's call the distance from here to here D1, and from here to here D2. Okay, any questions? So I'd like to start with free body diagrams. So this is the free body diagram. So let's write the corresponding equations. So first I want to write for particle number 1. So let's write for the horizontal components. So horizontal component of this guy is this guy, plus horizontal component of this guy is this guy. So it's going to be T cosine θ1 plus F sine theta phi. Phi, remember, I call this angle phi, which should be equal to this angle phi. And this should be equal to M1G. And this was the vertical component. The horizontal component is going to be like what? It's going to be T1 times sine θ1 should be equal to F times cosine phi. So this is particle number 1. Let's do the same thing for 2. So, okay, this is T1. So this is going to be T2 cosine θ2. Now, so this guy, this force is in the opposite direction. So I need to write a minus. So this is going to be minus F sine phi. And this should be equal to, again, M2G. And the horizontal component is going to be T2 sine phi, right? Yes. Sine θ1 or θ2. Okay, let's take a smaller one. T2 sine θ2 is equal to F cosine phi. Okay, these are all the equations, right? Any other equations that I couldn't write here? Anybody wants to add anything? So now, after yesterday talk, I think I noticed that was a little bit too complicated, so I had to simplify this. Actually, you can manage this to some extent, but I think it's not pretty. So I want to remind you all the unknowns. We have a lot of unknowns here. T1, T2, we don't know F, we don't know θ1, we don't know θ2, and we don't know phi. So this is a lot of unknowns. How many? 1, 2, 3, 4, 5, 6, and we only have 4 equations. So we better simplify this a little bit. And the simplification is coming from small angle approximation, right? Let's take all angles small, okay? All angles are small, theta 1, theta 2, and phi are all small. Then this guy, cosine of a small angle is 1. Sine of a small angle is the argument, like sine phi is equal to phi for small phi. Sine theta 1 is equal to theta 1 for small theta 1, and so on, right? Let me write all these equations with that approximation. So this is T1 plus F times phi is equal to M1G, and T1 times theta 1 is equal to F. So this is T2 cosine theta 2. Okay, this is not cosine because this is small angle. This is 1 minus F times phi is equal to M2G. And finally, T2 phi 2 is equal to F. Okay? So here, I want to do one more approximation. I want to consider the case in which phi is actually much, much smaller. So this guy, I want to completely neglect that. And maybe you can ponder if you can take this term into account later if you have the appetite. But let's do this. From this now, okay, we see some stuff, right? First of all, F is equal to T1 times theta 1, and F is equal to T2 times theta 2. So from this, we can already get what T1 theta 1 should be equal to T2 theta 2. And from the other two equations, so T1 is equal to M1G, T2 is equal to M2G, right? So let's write this. So M1 times G times theta 1 is equal to M2 times G times theta 2. So if you clear these guys, you have what the question is asking. So theta 1 over theta 2 is equal to M2 over M1. Okay, that's the first result. Maybe I can box this in. Is this restricted to degree? Yes, maybe even less than that, right? I think maybe around, definitely less than 10 degrees, but maybe even less than that, a couple of degrees. So these, in reality, these two masses are really close together, right? They're almost touching. Yeah, I mean, you can actually, like, I suggest you go ahead and plot theta versus sine theta, right? You know all these computer resources, you know how to plot things, and look at the difference. Sine theta minus theta is a function of theta. And look, like, say, if you need 1% accuracy, what is the largest theta? Okay, you can look for that. Okay, now let's continue. Like, this is not the end of the problem. So the problem was asking theta 2, theta 1 over theta 2, but we also are asked to estimate the distance between spheres for each case. We are asked to estimate this distance or this distance. Okay, so let me try to write an expression for this, and let's see if we can get anything. So first, the distance that we are required to calculate is d1 plus d2, right? And this d1 plus d2 is equal to what? So for small angles, this guy divided by this guy is sine theta 1. Sine theta 1, maybe I can write it like this. d1 over L for small angles, or theta 1 is approximately d1 over L, okay? And I can write the same thing for the other guy. Then d1 is approximately theta 1 times L. Let's write this. So d1 plus d2 is equal to L times theta 1 plus theta 2 is equal to. So I need to find something to write this. And for this, I need to write the only thing that I didn't use. And I didn't use electric forces, right? So in the electric forces, you can look at any angle here. For example, you can look at this one. Let's write, maybe I can write it like here. Tangent theta 1 is approximately, it should be equal to what? So for example, this is approximately like this, right? Maybe this is like that. It should be like, how should I do this? T, maybe it's like opposite divided by the closest, right? And the opposite is equal to F, for example, for this guy, and divided by closest it M1G. So this is approximately equal to what? Actually, I want to also do small angle approximation here. This is theta 1. So this is equal to K Q1 Q2 divided by D1 plus D2 squared. And I can write the same thing for the other one. Theta 2 is approximately K. Okay, there's also M1G. K Q1 Q2 divided by M2G D1 plus D2 squared. So then this whole thing is equal to L over G. Now I'm just copying what I just found for this. So I just wrote LL. I just wrote this guy. And let me write K Q1 Q2. And do I have everything? This one divided by D1 plus D2 squared. Remember the distance between these guys is D1 plus D2 squared. This should be equal to, okay, also, did I forget something here? Yes, I forgot something like this. 1 over M1 plus 1 over M2. Okay, so let's put these guys to here. And let's put this guy to here. Now I can look at this equation. I have an equation for D1 plus D2 in terms of D1 plus D2. I can take D1 plus D2 squared to here and take the root cube of both sides. Then I will get something like this. D1 plus D2 is equal to L over G K Q1 Q2, and let's write this like M1 plus M2 divided by M1 M2 and take 1/3. And that's the final result. Okay. And for this, maybe you can do the rest, right? You can put the cases. A, put Q1 is equal to Q, Q2 is equal to 2Q, M1 is equal to M2 is equal to M, and B also put Q1 is equal to Q, Q2 is equal to 2Q, M1 is equal to M, M2 is equal to 2M, and let's see what you get. All right, let's continue. So a thin rod is bent. Let me close this. A thin rod like this is bent into the shape of an arc of a circle of radius r and carries a uniform charge per unit length lambda. The arc subtends a total angle 2 theta, like this, theta, theta, 2 theta. And it's symmetric about x-axis as shown in the figure. Determine the electric field E at the origin here. Maybe I can clean this up. So let me start. So I just first take like with what we do all the time. I just choose tiny little bit of chunk. And I look at the contribution of electric field coming from this chunk like this. Okay, something like that. And I say this angle is theta, then this angle is dot, 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 theta. And I write the electric field. So electric field is dE is equal to K total charge. Total charge is density times length. Length is R times d theta divided by total distance squared, which is R squared. Right? Now I found this, but I need to project this guy because when I sum over all these contributions, all the vertical components will cancel and I'll only end up with this horizontal component. So then I need to write the cosine here, cosine theta. Here theta is the angle which sees infinitesimal charge, right? Yes. Here is the theta. Here is the theta. And here is the d theta if you like. This is d theta. Maybe I can write it a little bit bigger so that you can see. So this one is theta, this guy. And I need to write an infinitesimal here. Let me write it like this. Maybe I can use a different color. So around this angle, I put just if infinitesimal width, this, and I call this d theta. Okay? Does lambda times r times d theta mean q? Yes, that's total charge. Exactly. Here is dq, charge. Okay. So how do we take this integral? Yes, right? We can take this integral, right? First, let's clean this up. R cancels, and all of these guys, k, lambda, or these are constant. They don't depend on integration variable. So we can just take it like, oops, take this. Ex is equal to k, I don't know, lambda divided by r, integral d theta cosine theta. And integral limits is like minus theta 0 to theta 0. And we can take this integral. It's like k lambda r. It's like sine theta, most elementary integral we can find, minus theta 0 to theta 0. And the result should be k lambda divided by r sine theta 0 minus minus sine minus theta 0, but this whole thing will be 2 sine theta 0. So this thing should be equal to E is equal to k lambda over r 2 times sine theta 0. Okay. So you didn't get, I didn't get why we wrote cos in the first place. We wrote cos because if we didn't write cos, we would have gotten this component here, right? It's like charge, k times charge divided by distance squared. It's going to be like this guy. But I know from symmetry for every chunk here, there's a chunk here like this. And their vertical components will cancel each other. So I need to project it to horizontal so that I can only sum over horizontal components. So that's why there's like a theta here. There's why we have a cosine theta here. Remember that there has to be a direction with the electric field. And for this guy, we put the direction information manually by using the symmetry. And we know that the total should be along this direction. So we project every single tiny contribution to this component and then sum. Show that at points along the axis of a dipole, along the same line that contains plus q and minus q, like along the same line that contains plus q and minus q, along this line, electric field has a magnitude like this. 4 are much bigger than L, okay? This is L. And if you are at a position where R, like this is R, show that electric field reduces to this. And the question is, in what direction does E point? If the point isn't at the origin. I mean, if the point is not at the origin, maybe you can try to do this and you'll see, you'll get some ugly integrals. Like if you are here, that kind of integral is not as nice. It's still pointing this direction, but you know, I challenge you to work out that integral. Or if you are here, it's the same kind of story. Because here the integral is really nice. These r's cancel and they are independent of angles. Imagine you are here, I'm not sure, right? Every point, there will be a angle dependent distance here. And that kind of, it could be simple. I didn't work it out, but you should do it if you are curious. So let's work this one, okay? I want to, let me just choose a point. Let's choose something like that. So let me call this distance, what is it? R. And I want to calculate electric field here. So first, the direction. I think there will be two directions, right? One coming from positive like this, and the other one coming from negative. But positive and negative are the same charges, same magnitude charges. So, but their distance is just a little bit different. So the total net, so this guy is going to be bigger than this guy. So the net electric field is going to be pointing this way, okay? Maybe I can write it like this. So this is E total. And for this, let me write each contribution separately. So E is equal to, again, K plus Q divided by distance, which is R minus L over 2 squared. Am I right? I think so. This is the first one. KQ this minus KQ, I'm writing the contribution coming from this guy, divided by R. Now this is R plus L over 2. L over 2 and squared. Okay. Now I take K times Q. Okay, let's do some algebra. Open bracket. So this is going to be R plus L over 2 squared minus R minus L over 2 squared. And this is divided by R minus L over 2 squared, R plus L over 2 squared. Close. I think now I can, for the numerator, I can do this. This guy is going to be what? So it's like A squared minus B squared is equal to A minus B, A plus B. And this will give me what? R plus L over 2 minus R plus L over 2 times R plus L over 2 plus R minus L over 2. and this thing is equal to, okay, this one cancels with this one, L times this one cancels with this one, 2R. And for the denominator, it's already like a large power of this, so I'll neglect this L. So what I'll end up is, so this is the condition R much larger than L, then K Q L times 2R divided by, if I neglect these guys and these guys, this is R squared plus R squared R to the fourth. This is R to the fourth. Cancel 4 with this. This is cube. And now I want to write this as, so this guy as P. Then the result will be K. Maybe we can also open up what K is, because that's the question. This is 1 over 4 pi epsilon naught. So this is going to be 2p divided by r cube. Okay. All right. One more. Ready? All right. So this is the last one. An electron moves in a circle of radius r around a very long uniformly charged wire in a vacuum chamber, as shown here. The charge density on the wire is lambda is equal to 0.14 microcoulomb per meter. And the question is, what is the electric field at the electron, the magnitude, and the direction in terms of r and theta, r and lambda? And B, what is the speed of the electron? So I remind you, I think I already emphasized this in several occasions. So this is like an infinite long straight line, and electric field around any point will be radially outward, right? Something like this. Or if you are here, it's going to be radial outward. Something like that. And the magnitude, I think E, something like this, 1 over 2 pi epsilon naught lambda over r, right? That was our result. But let me take this back. I want to write this in terms of K. So if I write it in terms of K, 2 lambda over r, and it is radially outward. So okay, that's all part A ask. So let's go to part B. What is the speed of the electron, right? How do I get this? Does anybody remember what we can use here? So this is A, and the B, speed, exactly, right? Centripetal force, right? So force is equal to charge of an electron times electric field, and this should be equal to m velocity squared, circular motion formula, exactly, mv squared over r, right? Right? So let's write this. It's going to be E. I just plug in what I got for E. It's like K times 2 lambda divided by radius should be equal to m v squared divided by r. And if I cancel these, I have something nice. So then I can solve this for V. V is equal to, let's say 2E K times lambda, maybe M here, and the whole thing square root. Is that correct? Did I miss anything? Hopefully not. So we actually solved this problem very carefully. So we said, if you have an infinite line of charge density, we can take a little chunk here and we can calculate the electric field here, right? And we said for every point here, there should be another point symmetrically placed here. And you can write the electric field for this guy. And if you look at these 2 points together, this component plus this component, their verticals cancel. So there's only horizontal. That's why electric field around the wire is always, of course, if the wire is infinitely long, is always radially outward. So if you have a wire, if you want to find the electric field at this point, you can just draw a circle and electric field will always be like this. Exactly, the negative charge doesn't stick on the rod. Why? I should actually ask you. What keeps the negative charge from sticking? Why would the charge just circle but not just fall on the like positively charged rod? What keeps that from happening? So okay, if you see the satellites on TV, like satellites, they are circling Earth. What keeps them from falling? Why those satellites up in the space don't fall on Earth? Yes, right? Their speed. Exactly. So I think we spent quite a lot of talking this point in the first semester, but the idea is they are actually falling. We can say they are falling, but this circular motion they are performing is kind of like a free fall. But so the same thing happens here, right? This electron is experiencing some sort of force, but this force by itself is not sufficient to determine, right? There's also like velocity, so it just actually circles around. And if you like, it doesn't fall. I mean that's like a bad language because it actually falls. Maybe in the high school they teach you something like this. Oh, there's like force like this. There's like centripetal force like this. So they cancel this. Why it doesn't fall? That's wrong. I think we spent a lot of time to erase that misinformation. The correct way of thinking is like there is like centripetal force, and that centripetal force gives rise to an acceleration, and this acceleration is like circular acceleration. So this guy is performing a circular motion. So maybe I can just put the numbers and get something for you to compare later. Let's calculate this guy. So this is 2 times electron charges, if I remember correctly, 1.6, so times 10 to the minus 19 Coulomb. And K is, we just calculated 8.99 times 10 to the, what was it? 10 to the 9. Lambda is equal to what? 0.14. Maybe I can pull this guy a little bit. I'm running out of space. Times 0.14 times 10 to the minus 6. So I got 2, I got E, I got K, and I got lambda. And I need to put the mass of electron, which is, let's put it here. M is equal to 9.1 times 10 to the minus 31 kilogram. And we can now close the root. Let's do this. Okay, let's check the units to make sure we didn't miss anything. So this one, so 8.99 should be, okay, Newton meter squared per Coulomb squared. Charge density is Coulomb per meter. This is Coulomb, and this is kilogram. So if we clean these things, okay, I have Coulomb squared Coulomb. I have meter here, this one, and I want to write Newton as kilogram meter per second squared. So this one, kilogram, you cancel with this one. So this whole thing becomes meter per second squared times there's one more meter here, meter squared per second squared. If you take the square root, meter per second. So the unit checks. So finally, let's take it like 4.4 square root 2.09 actually times 10 to the 7 meter per second. Okay, thanks for coming. I'll see you next time.